All right. It's a pleasure to welcome the last speaker of the morning session. It's Markus Lohrey from Siegen, and he's going to tell us something about streaming word problems. Markus, please.
Thank you very much. And yeah, thank you very much for the invitation to the seminar. I'm a bit embarrassed to speak 50 minutes. I think when I was asked, I said, I don't care how long.
You can stop sooner.
I can stop sooner, yes. We will see, maybe. All right, so yes, this is joint work with Lukas Lück. He was a master student in my group, and Julio Jochitemol, he is a PhD student. So what are streaming algorithms? Streaming algorithms are highly efficient algorithms, and they receive the input symbol by symbol. They receive a symbol, they immediately process the symbol, and then they receive the next symbol, and so on. And in this talk, I will approach streaming algorithm from a more automata theoretic perspective, namely via this notion of deterministic automaticity. And what is the idea here? The question is, how good can you approximate a non-regular language by a deterministic finite automaton? Deterministic finite automaton, I will always abbreviate by DFA. So that's the question, and let's directly go to the definition. So take a language L over any alphabet, let's say sigma, okay? And okay, the language could be regular, but the interesting case comes up when L is not regular, so when it cannot be recognized by a finite automaton, by a deterministic finite automaton. And then the deterministic automaticity of this language L is this function DLN. And what is it? How is it defined? DLN. It's the number of states of a smallest deterministic finite automaton. I call it DLN, this automaton, such that when you take the language L and intersect it with all words of length at most n, this is my notation for the set of all words of length at most n over the alphabet sigma, this is the same as the language accepted by this automaton, also intersected with all words of length at most n. Yeah. So basically, this automaton, you could say this automaton D sub ln. So it characterizes, or it accepts all words of length at most n correctly with respect to the language L. Okay. So that's the deterministic finite, the deterministic automaticity of the language L. Yeah, it's a function from natural numbers to the natural numbers. Okay, so that's the thing we first want to study. And some remarks. What is the connection to streaming algorithms? Well, you can view this automaton as a streaming algorithm for the language L. So it starts in the initial state of the automaton, and then the automaton reads the input word W in a single left-to-right pass. Yeah, that's what our automaton is doing. Yeah, a single left-to-right pass over the word, symbol by symbol. And if you know that your input word has length at most n, then after reading W, it accepts the word even only if it belongs to our language L. So that's roughly the connection to streaming algorithms. I will come back to this probably. Okay. In streaming algorithms, people are usually interested in the space complexity. And that's what we also want to do. And also the space complexity of the streaming algorithm can be nicely defined in this automata setting. Namely, the states of this automaton can be stored with binary logarithm of the deterministic automaticity many bits. Yeah, because this is the number of states that you have in the automaton, right? In the automaton DLN. And if you have DLN many elements, you can uniquely store them using binary logarithm of this number, many bits. Okay, so this is, and now we define the deterministic streaming space complexity of our language L simply as the binary logarithm of the deterministic automaticity of the language L. Yeah, that's basically the streaming space that we need to except the language L. Okay. So you see, I mean, in principle, I mean, there's no big difference between the deterministic automaticity of a language or the streaming space complexity. There's just this logarithm of 2. I mean, but in principle, it's the same concept. Okay. So some facts about deterministic automaticity. So it was introduced, it was introduced actually before this paper from '85. But Shallett and Breitbart, they were the first to study this notion of deterministic automaticity in a systematic way. And here are some results. So take a language L and consider its deterministic automaticity. Then the first thing is quite obvious. The deterministic automaticity is always bounded by alphabet size to the power of n. Because what you can always do is when you get your word of length at most n, the automaton can always store it explicitly. You store the whole prefix that you have read so far. If you take this as your state at the end, you can decide whether the word belongs to the language or not. This is a trivial upper bound. Actually, you can forget the big O here. If L is regular, then the deterministic automaticity is a constant. Because, I mean, if the language L is regular, there is one automaton, deterministic finite automaton, that works for all words of any length. So that's also a trivial statement. The next statement is non-trivial. It was proved by Richard Karp in '67. Namely, if a language L is not regular, then the deterministic automaticity of the language L is lower bounded by a linear function, more precisely by n plus 3/2. For infinitely many n, this is only true. It's always true. This is very interesting because basically it tells you that there is a gap between constant automaticity and this linear automaticity. Yeah, there's nothing in between. If you have a non-regular language, you immediately jump to this lower bound n plus 3/2. Okay. Now, in this talk, I will mainly be interested in a generalization of the deterministic automaticity, and I call it probabilistic automaticity. So again, the setting is the same as before. We have a language L over an alphabet sigma, and we define a function, and now I call it P sub L of n, the so-called probabilistic automaticity of the language L. And it's defined in a very, similarly to before. We define it as the number, the function PLN of n, or the value of the function on n, is the number of states of a smallest probabilistic finite automaton, P sub Ln. I will more say about how is it defined, such that for all words of length up to n, the probability that your automaton, P sub Ln, accepts W is, well, depending if W is L, then this probability is high. Let's say at least 0.9. If W is not an L, then the probability of acceptance is small, namely, let's say 0.1. So first of all, I should explain in more detail how a probabilistic finite automaton works on an input word W. And I define it in the following way. Basically, this automaton, PLN, is the same as a deterministic finite automaton, with only one additional ingredient, namely, this automaton has a probability distribution on the set of states. I call it rho. And the automaton then operates in the following. When it starts reading an input word W, the first thing it does is it guesses the state where it starts. It guesses the initial state Q with this probability, so rho of Q. That's the probability that you take Q as the initial state. And then you work as before, deterministically. Then the word W is read into the automaton. You start in the state Q with probability rho of Q, and then you operate like a normal, ordinary deterministic finite automaton. So basically, this means that all the randomness in the automaton happens in the very beginning. Once the automaton starts reading the word, there is no more randomness. And this is not a restriction. I mean, usually if you look into the definition of probabilistic automata, then they can also make random choices during reading the input. But we do not have this, but this is not a restriction, actually. We can prove a result that the probabilistic automaticity doesn't change a lot. Yeah. I won't explain this in more detail, but that's our model. Yeah. All right. Good. I should also say, why did I choose 0.9 and 0.1 here? This looks a little bit arbitrary. It is arbitrary. You can choose any other constant, and the definition also wouldn't change a lot. Only constant fact. You would only get some constant factors, nothing really crucial. Okay, so that's the probabilistic automaticity. And of course, the probabilistic automaticity is always bounded by the deterministic automaticity. That's obvious. But using the probabilistic automaticity, we can now define what I call the probabilistic streaming space complexity of the language L. It's the same idea. We simply take the binary logarithm of the probabilistic automaticity. And you can view this as the space that you need for a randomized or probabilistic streaming algorithm to correctly accept the language L with high probability. For every input, the probability that you give a wrong answer is small. With my setting, it's at most 0.1. Okay? Good. To make this a bit more clear, let me give you a simple example. Take this language L. You have a word W over the alphabet 01, a bit string, and the words in your language, they are of the form W, sharp, W. Sharp is a separator symbol. This is clearly a non-regular language, right? And let me explain why the probabilistic streaming space complexity of this language L is logarithmic in N. So for this, I take an input word, X, I call it X. Let's take a word of length N over the input alphabet, 0, 1, sharp. And a probabilistic automaton now behaves as follows. If the input word X is not of the right, let me say, syntactic shape, namely if the word X is not of the form U, sharp, V, where, this must be a U here, of course, where U and V have the same length, let's say M, of course, this M must be N minus 1/2, then the automaton will reject. Basically, you check this in parallel when the automaton runs. Yeah, if it's not of this form, then you reject. And for this, you only have to count. You have to count. The automaton has to store the length of U and the length of V. And this can be done with log N many bits. Yeah, the whole string has length N. The interesting case is where the input word has this shape, U sharp V, where U and V have the same length. And then we interpret U and V as binary encoded integers, let's say with the least significant bit first. It's so important, but because the automaton operates from left to right. And then the automaton, and now the randomness comes into play. Namely, the automaton guesses in the beginning a prime number P with log M. Yeah, M is the length of U and V. Of log M many bits. Of course, M is at most N, so this is at most log N many bits that the automaton guesses. It guesses a prime number, and it computes U, which you interpret as a binary encoded integer. The automaton computes U mod P and V mod P. This can be done by reading the two words. And at the end, it accepts if U modulo P is the same as V modulo P. You can show using standard results about prime density. I mean, you do not need any sophisticated results in this direction. You can show that the probability of an error is very small. This can be shown. This is a simple example of a streaming algorithm for a non-regular language. And the space complexity is low. It's logarithmic in the length of the input word. Okay, good. Let me say something about one more aspect, namely our model of streaming algorithm is a so-called non-uniform model. This means for every input length n, we have a deterministic or probabilistic, depending on whether we are interested in deterministic or probabilistic streaming space complexity, finite automaton that handles words of length up to n. And in principle, the function mapping this input length n to the automaton for input length n can be uncomputable. And that means it's a non-uniform model. And that's actually the same as in circuit complexity where Armin was speaking about. There are also two variants. There's also the non-uniform variant where you have for every input length a different circuit, and the circuits have nothing to do with each other. Then there is also the uniform model where there is a simple algorithm that gives you the nth circuit. And here you can also study a uniform version of streaming space complexity or streaming algorithm where this deterministic automata for input length or probabilistic automata for input length n must be efficiently computable. Okay. Why do we choose the non-uniform setting? Well, lower bounds that are shown for the non-uniform setting are, of course, stronger. Yeah. And our streaming algorithm for specific groups, I haven't explained this, what I mean by a streaming algorithm for a group, but we will come to that. They are always uniform. Yeah. It's a little bit similar to circuit complexity. Yeah. Usually uniformity is not a big issue. Okay. So now let's come to groups. So this was about streaming algorithm, and here I can be probably a little bit faster. So the setting is the standard one. We have a finitely generated group. Sigma are the set of group generators, and that means there is a surjective homomorphism phi mapping words over the alphabet sigma to group elements, the evaluation homomorphism. And then the word problem here in this talk, I consider the word problem as a language, namely it's the set, so for the group G and the fixed generating set sigma, the word problem is the set of all words over the alphabet sigma that evaluate to the group identity. And there is the well-known result of Novikov and Boone that there are finitely presented groups with an undecidable word problem. Okay, here I have a slide with some complexity results for word problems, but I think most of it was already explained by Armin, and actually I don't need it. I gave this talk on a computer science conference before, so I wanted to give some background on word problem. I think I can jump over this. Maybe only this one result. This is important for us later. For finitely generated linear groups, there is this famous result of Lipton and Salkstein saying that the word problem can be solved in deterministic log space. Okay, now you might already guess I'm interested here in streaming space complexity of word problems. And the first thing I want to do is I will relate it to the growth in the group. So I guess you're all familiar with the growth function of a group. Again, take a group G with the finite generating set sigma. We have again this homomorphism mapping a word to the corresponding group element, and the growth function of G, I call it gamma. It depends on the group G and the generating set sigma. Well, it's simply the number of elements, group elements that can be represented by words up to length n. This is the growth function that I consider. Well, very well-known concept. Of course, it depends on the generating set, not in a very strong way, but yeah. And the first result that I want to state is that the deterministic streaming space complexity, I could also say the deterministic automaticity of the word problem is exactly determined by the growth of the group. So remember, the deterministic automaticity tells you how good you can approximate our word problem now by deterministic finite automata. And the first result says that the deterministic automaticity of the word problem is exactly the growth function at n½ rounded down, plus possibly 1 or 0 or 1, namely n mod 2, so 0 or 1. So basically, it's the growth function at n½ This is the first result. And the second result is about the probabilistic automaticity. And it's also, again, the growth tells you something. But this time, it's a lower bound only. The probabilistic automaticity of the word problem is lower bounded, big omega, lower bounded by the logarithm of the growth function, again, at n½ I won't prove this here, just give you an idea. For the first result, I mean, you wouldn't be probably surprised if there would be an n here, because the sphere, the ball of radius n in the Cayley graph can be viewed as a finite automaton, and this finite automaton, the ball of radius n, can be certainly used to tell whether a word of length at most n is the group identity or not. Yeah, that's quite clear. Why is n½ here sufficient? Well, the point is the following. Imagine you you have a word of length n, and you have the Cayley, the ball of radius n½ in the Cayley graph. And now you read in your input word of length n, and as soon as the word leaves the ball of radius n½ there is no chance to come back to the group identity, right? So therefore you can reject. As soon as you jump out of the ball of radius n½ in the Cayley graph, you can reject your input word. So this is basically the first point. Of course, this also tells us that, well, deterministic automaticity of word problems is nothing really new. It's exactly determined by the growth function, and therefore the deterministic streaming space complexity of word problems is also exactly determined by the group growth. For the probabilistic automaticity, the situation is different. Here I have only a lower bound, and this lower bound can be shown by communication complexity arguments. Maybe at the end of the talk I will come back to such an argument, but at the moment I want to talk more about upper bounds. Here I have 3 famous results on growth. Again, as I said, I gave this talk on a computer science conference, so I wanted to give some background. I mean, you know these results, Gromov's theorem. The growth is polynomial if and only if the group is virtually nilpotent. There is this Wolff-Milner result that if you have a finitely generated solvable or finitely generated linear group G, then there is a dichotomy. The group is either virtually nilpotent and then it has polynomial growth, or there is a constant C such that the growth is, it is of the form C to the power of n. Yeah, so the group has exponential growth. And there is also the Gregorian group as an example of a group with intermediate growth. Okay, now let's come to some concrete groups. And in the following, I will only be interested in the probabilistic streaming space complexity of groups. Because as I said, the deterministic case is basically done. We have this exact correspondence to the growth function. And let's first look at linear groups, finitely generated linear groups. And the first result is that if G is a finitely generated linear group G, G is twice here, then the word problem of G has probabilistic streaming space complexity big O of log n. I do not talk here about a concrete generating set. This is maybe also not surprising. I mean, the streaming space complexity depends somehow on the generating set, but not only in a superficial way. Yeah, it only affects constant factors, the concrete generating set. This is not surprising, probably, this result. Basically, to show this, you use the algorithm of Lipton and Salkstein. Yeah, they gave an algorithm working in logarithmic space on a Turing machine for the word problem of a finitely generated linear group. And you can easily make a streaming algorithm out of it. But for this, you have to guess prime numbers again. Yeah, you take the Lipton-Salzstein algorithm and it chooses prime numbers. It makes something for all prime numbers up to a certain length. And instead of doing that, you randomly guess a prime number and make all computations modulo this prime number. For nilpotent groups, the word problem even becomes log n, the probabilistic streaming space complexity, if you have a finitely generated nilpotent group. And it's again similar. You evaluate matrices. I mean, if you have a finitely generated nilpotent group, there is always a finite index group, subgroup, which is torsion-free, and this finite index subgroup can be embedded into a group of unitriangular matrices. And when you multiply those unitriangular matrices, you get only small numbers. And then it suffices to make all computation modulo a randomly guessed prime number of having only log n many bits. That's very roughly the idea here. And from this, we get a nice dichotomy for linear groups, namely, if we have a finitely generated linear group, then the word problem for G has probabilistic streaming space complexity, either big O of log n, namely in case you have a finitely generated nilpotent group, or big omega of log n. For this, I use these upper bound that I proved before and this dichotomy result of Milner and Wolf. Okay. Now, group operations are also interesting, of course. And if we have some groups where we have already efficient probabilistic streaming algorithms, we would like to combine these groups and get, again, a space-efficient streaming algorithm. And there can be something done, namely, take the class C. C is the closure of the class of finitely generated linear groups under the following operations: finite extensions, graph products. So not graph of groups, graph products, where you have groups, you take the free product, and then some groups are connected by edges in a graph, and those groups are allowed to commute, the classical graph product construction. And wreath products with finitely generated abelian groups on the left. The left factor of the wreath product must be finitely generated abelian. So in other words, if G is in the class C that I consider here, or that I define here, and A is finitely generated abelian, then the wreath product of A and G is also in C. Then we can show that for every group G in this class C, the word problem has a probabilistic streaming space complexity big O of log n. Basically, big O of log n is always the goal that we want to have. We want to bound the streaming space complexity, the probabilistic streaming space complexity, by the logarithm of the input length. I will say a few words about the proof in a moment, but let's first derive a corollary. By this final result here, or this final closure property under wreath products with a left factor, which is finitely generated abelian, we immediately get the fact that the word problem of a free solvable group has probabilistic streaming space complexity big O of log n, because every free solvable group can be embedded into an iterated wreath product of abelian groups, finitely generated abelian groups. Good. Then what is the main tool to prove these results here? The main tool are we call it I call it here distinguisher. In the paper, it's actually called different, but maybe distinguisher is a better term for this. What is a distinguisher? Take a finitely generated group G, sigma's generating set, and take a constant epsilon, a small constant. It's a small probability, actually. Then we take a sequence of probabilistic finite automata in the same way as I have defined it before. So the automaton guesses an input state, and then it proceeds deterministically. Pn is the nth automaton, and again, Pn is the automaton that will handle input words of length n, or up to n, let's say. Pn can handle input words of length up to n, and we call this sequence of automata an epsilon distinguisher for the group G if for all n greater equal 1 and all input words u and v over the generating set, sigma's generating set, of length up to n. So I take now 2 input words of length up to n. The following is true. We consider the probability, where the probability here is taken over the states of the probabilistic finite automaton. So maybe, here it's written. So the probability here in this line is taken with respect to a distribution on the states of Pn. That's the same setting as I had before when I introduced probabilistic streaming space complexity. The automata, the probabilistic automata, they are basically deterministic automata plus a probability distribution on the states of the automaton. And what is the event that I consider here? The event is the state reached from the initial state Q with the word U is the same as the state reached from the initial state Q with input V. And now this probability must be large, namely 1 minus epsilon, if the 2 words U and V are the same in the group. And it's at most epsilon if U and V are different in the group G. So basically, this distinguisher, it corrects with high probability, it distinguishes words that are not the same in the group, and it gives you always a correct answer. If the words are equal, then you will end up with high probability in the same state. If the 2 words are different in the group with high probability, you will end up in different states of the automaton. This is our notion of distinguisher. The space complexity of an epsilon distinguisher, it's always the same. You take the function mapping the input length n to the binary logarithm of the number of states of Pn. The same as we always had before. And now a simple observation is that if you have, again, a finitely generated group, which has a 0.1 distinguisher with space complexity S of n. This is the function which measures the space. And our constant epsilon here, we now set to 0.1. Then the streaming space complexity of the word problem is also bounded by S of n. I mean, you can, in a very simple way, it's not difficult. You can use this distinguisher to correctly accept the word problem for a given input word with high probability. Basically, you set one of the 2 words here, let's say V, to the empty word, and use this property of the distinguisher. That's all basically you do. That's a simple observation. So distinguisher are something stronger, right, than probabilistic streaming algorithms for the word problem. They are stronger in some sense. Actually, it's open whether they are really stronger, but that's another question. Now, what we can show now is that every linear group has a distinguisher, namely for every for every constant C greater than 0, there is a 1 over n to the power of C distinguisher with space complexity log n for a fixed finitely generated linear group. This is again basically the Lipton-Zalcstein argument. And then we can use, and that's the more interesting thing now, is we can use transfer theorems for distinguisher. Namely, if you have groups G1 to GK, K many groups, such that every GI has an epsilon distinguisher with space complexity SIN. They can have different space complexity. That's not important. And let C be greater than 0, be a constant. That's the setting. Then we can show that every graph product of G1 to GK has again a distinguisher. Let's forget this for a moment. You have again a distinguisher with space complexity big O of, well, what do you get? You get the sum of the space complexities of all the distinguisher for the factors of the graph product. That's not surprising because you run all those distinguisher basically in parallel. And then there comes another log n enters here additively. And this log n comes from right-angled arcing groups. Basically, very, very roughly, what you do here to prove this result is you using the distinguisher for the groups G1 to GK. Using those distinguishers, you can replace every group G1 to GK by Z, infinite cyclic group. Yeah, and with high probability, you do not make a big error by doing this. And then you have a right-angled arcing group, and right-angled arcing groups are linear. And by the first result, we have a log n space distinguisher. This gives you this log n here. Now the error, the epsilon, yeah, here we have a very small epsilon. The epsilon gets larger, and quite a lot actually, because what the new epsilon here for the graph product distinguisher is K. This is not so important. The K is just the number of factors in the graph product times n square times epsilon divided by 2 plus this additional small term. The main problem might be this n square here. N is the input length, and it gets larger and larger. So in particular, I mean, if the n becomes too large here, this gets larger than 1. But this epsilon here, or epsilon, let's call it epsilon prime here, this should be actually a probability. And if the probability is larger than 1, everything becomes trivial. But the point is the following. If we start with the linear groups, then you can make the epsilon very, very, very small, 1 over n to some constant. And this, if you make it, let's say n over 1 over n to the power of 3, then the n square is not so bad anymore. Yeah, you still get a small number, much smaller than 1, right? So this is the idea here. We have also a similar result for Reith products, namely, if G is a finitely generated group having an epsilon distinguisher with space complexity S of n, and A is a finitely generated abelian group, and epsilon prime is another small constant, then the Reith product of A, Reith G, has a distinguisher with this error probability, K. What is the K? I don't know. I think it's another constant, not so important. Yeah, the K is another constant that depends on the abelian group A. I think it's the number of cyclic groups. Times 2 epsilon n square. Again, there's this n square here plus epsilon prime. And the space complexity is, again, it only goes up moderately. Namely, you take the space complexity Sn of the base of the right factor G, and then there's another log n factor here, an additive log n part. I should say that these are transfer theorems. From a distinguisher for G, you get a distinguisher for the Reith product of A and G. And similarly for the graph products on the slide before. We do not have such a transfer theorem for the deterministic, for the probabilistic streaming space complexity. But we have it for distinguisher. That's the point. That's why we need this distinguisher actually to do basically the construction, yeah, to get these transfer theorems. But as we know, the distinguisher then can give us a probabilistic streaming algorithm for the word problem, yeah, of the same space complexity. Yeah, that's what we showed before. I gave some very high level proof here, but I see I have only 10 minutes, and so therefore I will jump over that, and I will say something about lower bounds for the probabilistic streaming space complexity. That might be also interesting. Let's take on what are the results. The first result is about Reith products again. Take a finitely generated non-abelian group H and a group G, which is just finitely generated and infinite, can be anything. Then the Reith product of H and G has probabilistic streaming space complexity theta of n, so linear. So basically that's the worst that can happen, right? Linear streaming space complexity. That means you have to store basically the whole word, the whole input word. You can do nothing essentially better than storing the whole input word. This result is interesting because as I said before, if H, here H, it's important that H is non-abelian. If H is abelian, then we have the result from before, the upper bound, which says that the streaming space complexity is only by this additive log n term larger than the streaming space complexity of G, the probabilistic streaming space complexity. So this gives you, so for graph products, we pretty much know what happens. A nice application is Thomson's group F, because it's known it contains a copy of the Reith product of F itself with F. Yeah. And since F is non-abelian, it follows that the word problem for Thomson's group F has probabilistic streaming space complexity theta of n, so linear. So the Thomson's group F is a nice example of the worst probabilistic streaming space complexity that you can get. You have to store everything, basically, the whole input word, in order to decide at the end with high probability whether the word is trivial in the group or not. Okay. On a Turing machine, the best known, I think this was mentioned probably also by Armin, the best known streaming space complexity is log n square. I think Armin talked about the circuit complexity, but it's basically the same reason. We have also a lower bound for Grigorchuk groups, namely, we can show the probabilistic streaming space complexity of the Grigorchuk group is lower bounded by square root of n, and even the deterministic, yeah, well, this is clear. The deterministic streaming space complexity is upper bounded by n to the power of 0.768. The second result comes simply from the best known bound on the growth of the Grigorchuk group. But this lower bound here is more interesting. And I want to say something, how can we prove these lower bounds on the probabilistic streaming space complexity? And that's where communication complexity enters. And I will give you only the basic ideas. There are more slides, which I will also jump over. Communication complexity is a branch of complexity theory where you can actually prove lower bounds. Yeah. And I will show you one concrete problem, namely disjointness. The setting is the following. We have two parties called, as usual, they are called Alice and Bob. And Alice has a private bit string A of length n, and also Bob has a private bit string B of length n. And their goal is they want to find out whether there is an index I between 1 and n, such that the ith symbol in A, this is the ith symbol of the bit string A, is the same as the ith symbol of the bit string B. And they are both 1. Yeah, there are 2 1s at a matching position. So that's why is it called disjointness? Well, this basically, I mean, you can view this bit string as a set, the set of all positions where you have a 1 in the bit string. And similarly for B. And this condition simply means that these two sets are non-disjoint. Okay, so they want to find out this, and they cannot do everything. They have to stick to a protocol, and in this protocol, they can exchange messages. Yeah. Alice can send some bits to Bob, then Bob makes some internal computation, sends some bits back to Alice, and so on for several rounds. Moreover, since we talk here about randomized stuff, randomized communication protocol, both Alice and Bob can use their private random coins. They can use randomness. They can make random decisions. And at the end, in the last round, Bob outputs a bit, I call it beta, 1 bit. That's the output of the protocol at the end. You could also say require that Alice gives the output, that doesn't matter. And the following must be true. If this disjointness property does not hold, so if there is a position I such that at A and B, I have at position I a 1, I can simply say the product of AI times BI is 1, then the probability that the output of Bob is 1 is high, is 0.9. The probability for that is high. So with high probability, Bob will output the correct answer. The probability is taken over the random choices of Alice and Bob. They make random choices, and this gives you at the end a probability distribution on the output of Bob. If A and B represent disjoint sets, so if for every position I, so if for all positions I, the product of AI times BI is 0, which means if you view A and B as two sets of position, the set of positions where 1 is located, then the two sets are disjoint, then the probability that the output, Bob's output is 0 is again high, with probably 0.9. So you see in both cases, Bob with high probability gives a correct answer. So that's a randomized communication protocol for disjointness. And people have studied this for a long time. And this is a very, very difficult result. It was proved by Kalyana Sundram and Schnittger in 92. And at the same time, it was also proved by Alexander Rasborov, also in 92. Namely, every randomized communication protocol for disjointness must exchange a linear number of bits. So basically, you could also say the best Alice and Bob can do is Alice sends all their input bits to Bob, and then Bob checks whether there is this matching one. That's an optimal protocol. You cannot improve much. Maybe a constant factor, but nothing substantial. And that's what we use in order to prove all these results I mentioned here before on these lower bounds on the probabilistic streaming space complexity of groups like Thomson's group or Reith products. Yeah, basically the argument is always the same. If we have a probabilistic streaming space complexity, for instance, for Thomson's group F, then we can misuse this protocol. We can use this probabilistic streaming algorithm for the group to get a protocol for the disjointness problem. Okay, then let me conclude with, so this is the proof, but again, I will, of course, jump over it. And let me come up with some open problems. I think probably the most interesting problem is whether hyperbolic groups have probabilistic streaming space complexity big over log n. I don't know. Another interesting case might be Baum-Slack solitaire groups, non-solvable Baum-Slack solitaire groups. Solvable Baum-Slack solitaire groups are linear. Then we have a log n space probabilistic streaming algorithm for the word problem. But for non-solvable Baum-Slack solitaire groups, I don't know. Another interesting thing is if you want to do some quantum computing, you can look at quantum streaming algorithms for word problems. In this setting, the algorithm doesn't store classical bits, but qubits, quantum bits. And there might be interesting questions. For instance, it's known that there is a quantum communication protocol for the disjointness problem, what I just considered, where only square root n many bits are exchanged. So this lower bound, this linear lower bounds, or the number of bits that are exchanged, no longer holds. This protocol uses this Grover algorithm for quantum searching algorithm. All right, I think that's it. I'm done. Thank you very much for the attention.
Okay. Thank you, Markus. Let us thank the speaker. Thank you, Markus. All right. If there are any questions to the speaker, so you're welcome to unmute yourselves and ask the questions.
I have a question about Grigorchuk group. You cited some estimates. I haven't quite followed. Doesn't your result follow simply from lower bounds for Grigorchuk group? And then you cited some very old estimates for the growth.
Which one is old? This
N0. Well, nowadays lower bound up to epsilon is the same as upper bound. So.
Oh, really? Ah, okay. I didn't know. I didn't look carefully enough. So
what I wanted my own results, but it's my joint result with Tiana Jenkins. It's really
okay.
almost the same.
Yeah. So what I wanted
the results, you only need this lower estimate. So far as you have x and to the alpha, you did use your estimate. Is it right?
So sorry. So this second point here is this upper bound is really you take the best upper bound for the growth of the Grigorchuk group, and then you take the logarithm. That's it. And is this still the best upper bound of Laurent Bartholdi, the paper?
But since the lower bound is almost up to epsilon the same as the upper bound, so
okay, sorry. Yes. But this is another point. Yes, this n to the power of 0.5 doesn't use this lower bound.
So it doesn't use it. So
it doesn't use the lower bound. No. Maybe one can improve it. I mean, I'm not the expert really in these arguments. It uses this subgroup K. It's usually called K, I think, of Grigorchuk group. Yeah, and that's used for this to get this lower bound here. Again, I mean, the argument is you use again this communication protocol for disjointness. Yeah, but yes. We don't use the lower bound, right? We only here for the second result, clearly we use the upper bound, and this uses this, I think it's this finite index subgroup called K of the Grigorchuk group. Yep.
And this lower bound, is it true more in general, let's say under what assumption you can prove? For example, general lower bound of Grigorchuk in the 80s, this x 0.5 holds for all residually nilpotent groups. Residually,
yes.
let's say.
Yeah, so you mean whether this lower bound here
would be true for all, let's say, residually important groups or something?
I don't know actually. I haven't thought about that. That's a good question, yes, but I don't know.
Yeah, thank you.
Yeah, I have to check the arguments for the lower bound, of course. Yeah.
All right. Any other questions or comments? Okay, if not, let us thank the speaker again. Thank you, Markus. I'll stop the recording.